section in the physical evidence where we start talking about clandestine drug labs, and you look at all the paraphernalia that go along with synthesis of drugs. But right now we're in the chemical evidence section, and so this is the first part where we talk about the chemical evidence that you would get to indicate substance of drugs of abuse or controlled substances. And so we're going to be talking this morning about colorimetric drug analysis. So these would be spot tests or developers you put on, and then it reacts with the drug and creates a colored center that indicates that you have a controlled substance. So a lot of these will be color dependent, and so that you will need to have some way to analyze the color and compare it to other colors. So you might spray it on there and it says if it's, say, if this is methamphetamine, it will turn orange. If it's other kinds of amphetamines, it might just turn brown. And so you've got to be able to distinguish between orange and brown, which may be more difficult than it sounds, because orange and brown are not that different. And you've got like UT, burnt orange. It's like a brownish orange, you know. So this color area can be problematic. So we'll dive into this today. Okay, just making sure that the recording is going. And so we have this, say, evidence from a clandestine drug lab. This is, let me just start here before we get into any of the spot tests. This is something that is I would say, a national danger. And if you ever have a grill, a propane grill in the future, and you're doing what they call the bottle exchange, which is a really convenient way now to get things filled. They have them just right down the street at the convenience store. You go there and you give them your empty. You pay for the new bottle, they give you the bottle. You don't actually own the tank, you're just buying the propane. And so you just keep exchanging these tanks. We do this in our labs too. We don't own any of those cylinders. We're renting them at $7 a month. We buy the gas that's inside. And so they have on contract how many of those cylinders we have, and every month we pay $7 for every one of those cylinders. That's why we get upset if the students just leave it empty and it's sitting in the lab. You need to get rid of those things. We're paying rent on those cylinders. So, but the thing is, if you go and you get a propane tank from the facility and the brass fitting is blue, you need to tell them, I'm not accepting that one. In fact, they need to flag it and take it and get it inspected on the inside. Because this is evidence that this tank has been used for a gas other than propane. And in fact, the blue comes from the gas. It's a reaction of that gas with the copper inside the brass valve. And this can be extremely deadly, especially if there's still this gas inside. So what do you think this substance is that reacts with copper? And this is your inorganic class coming up there. Mm-hmm. Okay, it's a coordination compound. And you can look at all of these different colors of solutions, aqueous ions. Okay, and it's the copper in this valve. And in fact, if you add ammonium hydroxide to these, just a little bit, those ammonia ions will attach to that copper and make even more blue substance. And so it's this copper ammonia complex that's deep, deep blue here on this valve. And so when people use these tanks to store anhydrous ammonia to use in the synthesis of methamphetamine, they're using it for a use it's not intended for. So you wouldn't store ammonia in a tank that had brass valves. You'd use stainless steel valves because it won't react with a stainless steel. But they don't care. They just want to steal some ammonia from a fertilizer truck out in the country and use that for the drug lab and then pitch this tank or turn it back in. And you see this corrosive effect of the ammonia. Well, that valve could be really corroded on the inside. And so then where the threads are and everything might be weakened. So you go to turn on the tank and the valve pops off and then you get a blast of ammonia in your face. And if you breathe enough of this in, ammonia or like chlorine gas or whatever, it gets in your lungs and you pretty much cough yourself to death. You have a water-soluble substance inside a little membrane that's water permeable, your lungs, your air sacs, and your bloodstream, just with osmotic pressure, will try to dilute those water-soluble substances in your lungs. And so you get what's called chemical pneumonia or pulmonary edema. So water gets in your lungs, and you're trying to cough this out, and you just can't stop. So that's how a lot of people die with ammonia gas exposure or chlorine, like they mix ammonia and bleach, and they get chlorine gas in their lungs, and then they get chemical pneumonia and pretty much a coughing fit until they pass. So I just wanted to say, since we're in the color change area, that this is an indicator that this brass valve has been in contact with ammonia gas. And so you would need to alert whoever's in charge of those tanks that they've got a problem with this one cylinder and they need to set it aside, not sell it, tell the manufacturer. It's probably not going to happen because the manufacturers are going to see that and they're going to know about it. But just something to be paying attention to. So let's look at these different colorimetric tests. These, changes in color and precipitation, these are ancient chemistry methods. And yet here we are in the modern day with all these analytical tools. So why would we still use the spot tests and even sometimes precipitation when we could just throw it on a GC or a ICP? And so a lot of times, these functional groups and these molecules are really crazy complex. And so we have some very advanced chemistry in today's slides. I'm not going to ask you to reproduce these reactions, okay? But I have highlighted some of the active areas, and there's some things that you can say, all right, that's based on dimerization, where you take two of these molecules, join them together, and now you have a colored substance, okay? There's different kinds of pigments and dyes, things that are colored, and they're going to be difficult to draw out. I'm not going to ask you to draw the structures, but there are 4 families of colored substances that we have, and I would like for you to know those 4 families. There's azo dyes, and we'll get to them. That's on a slide. There's carbonyl dyes. There's a thing where 3 aromatic rings or 2 aromatic rings are joined with a carbocation, and so you have this or a cation species, and you have an extended pi cloud. And again, that brings the transition down into the visible region from the UV. So a lot of these organic molecules absorb in the UV. They're not colored in the visible, but you join them together and you've extended the box. Remember the particle in a box. You've extended the box and the energy levels drop down out of the UV and now they're in the visible. So the homo-lumo gap has dropped down into the visible and you now have a colored substance. We could also use different acids and bases, but we use those for separations, but it's not really good for identification. Like you wouldn't say, I'm sure this is cocaine because it has a pKa of 9.3. Well, there's a lot of things that will have a pKa near 9.3. So acid-base might be useful for separations, but they're not going to be specific enough for making a call qualitatively. And so we're going to focus on just the chemistry in general in this slide, not the analytical methods. And so these are different ways to classify substances. We have over on the left a bunch of the substances that we talk about. We've got, you might have heard of GHB. It's a drug of abuse that's really difficult to detect. You see how it's such a small molecule, very water soluble. The half-life in the body is very short. So it's probably, I don't remember specifically, but it's like less than a day. And so unless you get a blood analysis very quickly, you're not going to see evidence of that drug. Here's morphine, and all of the opioids are going to have this 3-ring structure with this bridge on it, and that bridge has a basic nitrogen on it. And so this is going to be a basic drug. All of the codeines, heroin, morphine, they are all based on this opioid structure. Up here we have benzoylecgonine, and that's a metabolite of cocaine. So cocaine and its various derivatives are going to have this strange tropane structure. See, that's a very weird looking ring. And so when you see that structure, you know you're dealing with with cocaine or one of its metabolites. And so I've got these things on drug flashcards on Blackboard. And so I just want you to be able to recognize when you see this structure like this, that's cocaine or cocaine metabolite. I'm not going to ask you to draw those, but I just want it's just a simple recognition. say, oh, okay, I know that. That's what a cocaine-like structure. That's an opioid. If you were to see this fused ring structure, you know it's one of the opioids. So does it clarify kind of what my level of expectations are? You know, if you just walk in on a talk and they're talking, you say, oh, okay, we're dealing with opioids. You know. Down here, the testosterone, and these would be the anabolic steroids. Again, a lot of fused rings, but not a lot of aromaticity. And then here we have this 3 fused rings with a tail. These are all of the cannabis type compounds. So CBD and THC are going to have this kind of structure. And so these are all in their neutral form. You have some that are acidic, like this one's got a removable proton up here. This one has a basic nitrogen, and so on. Then you have this sort of artificial barrier between alkaloids and non-alkaloids. A lot of times the non-alkaloids, another word for that is synthetic. And so these are drugs that have been synthesized in a lab, but now we have these things called semi-synthetics. They're a plant-based material that's been modified in the lab. And so the dividing lines are kind of gray. And so it's not a lot of things I can specifically ask about, although the plant extracts are going to be alkaloids. And so cocaine's a plant extract, heroin, and all of these different here, the LSD. So these are alkaloids. They're historically plant extracts. So there's just, the point of this slide is just to kind of show you some of the structures, but also to say that it's classifying the substances can be tricky, because some start as a plant extract and then they're modified in some way and they become a semi-synthetic. Acids and bases, well, you know, that may be helpful, but it's not everything. Okay. And so we're just going to focus on the chemistry of the substances. Now, one thing missing from this list and also missing from the drug flashcards, which I'm going to add, and so you'll see a thing that says updated, and it'll have the fentanyl and fentanyl analogs. So that's really blown up in terms of number of times it's showing up in evidence. They're adding these tranquilizers and sedatives that are incredibly strong to drugs to mask the absence of some of those drugs. So they'll mix in a little fentanyl to make the drug stronger, have a stronger effect. And then they've gotten into some of these analogs that are much stronger than fentanyl. So this is a poster that Madison Shackmuth is putting forward at the forensic science meeting, and she and I are co-authors on it with Dr. Bazzini, and it's on the Raman spectra. So she took the research course, or not the research course, the graduate course in spectroscopy, and then used that in her research and simulated the Raman spectra of all the fentalogs to see if there are differences in the Raman spectra. But my point today is just to show you all of the structures of the analogs. So here's the fentalogs. And one of the things that I want you to be able to do is, if you're in forensic science and you look up the fentalogs, this is probably what you're going to get, is a figure like this. And so this is the question that I have for you. Can you use this above figure to draw the structure of all the analogs named to the right? Because this is what you're going to get. You're probably not going to get the structure of each one. Now, you might be able to find it in the Merck index or something like that, where you have each one individually listed. But a lot of times, just for space considerations, they use all of these little shorthand methods, R groups, which you should be familiar with from organic. But even then, there's some things about this figure that you need to pay close attention to. So here's the base structure. And so let's just make fentanyl out of this base structure. So this is the base structure, which go ahead and draw that base structure, but leave the R groups off. Just draw sticks where the R groups are. And then we're going to add on the pieces that go on those different R groups. So I'll do this on the board. Let's do one. Okay, so this is 1 and 3 and 2. So if you'll notice, for all of these structures, you've got all these different colors. And let's just look at R2. R2 is either equal to this long chain with a phenyl group on the end or a hydrogen. But the yellow is the only structure that has the hydrogen there. So norfentanyl. All the other structures have this ring with the long tail. Okay. So let's go ahead and draw that on there. And then 3, we have 2 options. So only in the pink structure do you have a methyl group. So that's cis-3 methylfentanyl. So only in that structure do you have that methyl group. All other structures you have the hydrogen. And so we're just going to, you could erase that stick, because if it's not showing anything, that's assuming it's a hydrogen. Okay, so let's do that. And then let's put the R group for 1 on there. So up here, these are the ones that change the most. And so we've got a green structure, the blue structure, a purple, gold colored, and this sort of brick red. And then all the other structures that aren't listed here by these 5 colors would have this R1, the base fentanyl structure. So it's going to be a ketone. We'll draw this, oxygen, and then an ethyl group on the other side. So that's the structure for just fentanyl. And if you change these different R groups, then you're going to have all of the other analogs. Could you have done that? Now, hopefully you can, if you couldn't before. Now you should be able to take, if you look for isobutyryl fentanyl, so this little orange colored one, the only thing that changes is up here at the top. And so if I just change this now, I've got that gold one. It's isobutyl. Okay. But no, everything else is the same. Okay. If I were to change that to the purple one, it would be this. Okay. All these other 2 structures are the same. So that's how you would draw all the different fentalogs. Just looking at that R chart and figuring out what different substances or what different functional groups are on the different positions. Okay. And so they all pretty much have the same structure, aromatic ring, nitrogen, like a cyclohexane, but with a nitrogen in it. These are all CH2 groups. And then this tail, and there's a couple of analogs where the tail might be missing, and you have a methyl group here, but then all of these different pieces up there. So if you saw this structure, you would know that's one of the fentalogs, the fentanyl analogs. It's going to be different than cocaine, different than the opioids, different than cannabis and THC. So good. Hopefully that you'll be able to do that. And so let's talk now about the color test. So we have all these different drugs. Their chemistry is incredibly complex. How are these color tests developed? I don't know. Okay, people are just, I don't know how you would just discover a drug test. You're just going to find, and you look at some of the reactants, they're absolutely crazy. So someone notices, wow, this reaction takes place and I get a large color change with this drug substance, then that might be useful as a colorimetric test. Then you go into development and see if you can find an easy way to distribute that and make sure that it's not in itself toxic or dangerous. And so then you have a color test. They're used quite a bit. I said 86% of the labs, this was when the previous book was written, so about 10 years ago, this survey, they said they used this Levine test for marijuana or cobalt thiocyanate for cocaine. There's a Marquis reagent for the different opiates, and then this PDMAB for LSD. Those were spot tests. Now, spot test tells you it's presumed to be these drugs. It's not confirmatory. But you can do a spot test and say, okay, I think this is an opiate. Then you can clean up that sample. Maybe if you do a liquid-liquid extraction to isolate the analyte and then run it on a GC or an LC, you would get a confirmatory test. Or if you could somehow separate it and then precipitate it out again, you could run it on an FTIR as a powder. The thing that's nice about these is they're very sensitive. So it doesn't take much sample at all to get a color change. And so a lot of times these are wipe-based. So I want to know if this surface has been contaminated with the drug of abuse. I can wipe the surface quite a lot, and I've concentrated all the particles on a small wipe. And then I can spray the developer solution, and it can change color. So I could say we've got a presumptive test for contamination with opiates. And so, there were opiates handled on this desktop. It's, again, not confirmatory. I don't have enough sample to run on a GC or anything, but it could be evidence. Example of that too is, a kid's got a crack pipe hanging from his rearview mirror. It's drug paraphernalia. He says, "Oh, I never used it." Okay, well, you could take a drop of methanol, swish it around in there, pour it on a wipe, let it evaporate, spray a developer on there, and see a color change and say, "Oh yeah, it has been used. There's methamphetamine on here, or cocaine, or what have you." A lot of times too, you remember in PCHEM when we were doing the benzene and the chlorobenzene lab, I had that little thing that screwed on the ATR that had a cup on it. And so you can take a very small amount of methanol, like this crack pipe example, put 2 drops in there, shake it around, and pour that onto that little cup, and the solvent will evaporate, and all of the residue from the inside of that pipe is now concentrated on the diamond. And so they call it extraction to disc, the diamond disc. So they can extract the interior surface of all of that little pipe and put it into a very small space, and your sensitivity goes way up because you've concentrated your sample. And that's a really handy technique and another use of the ATR. But we're still talking about color tests. So the detector for a color test is your eye. Now they do make some things that you can read with the standard light source and detector, but most of the time we're looking just with our eye. So you spray a developer on there or do some sort of reaction in a test tube and you see a color develop. And your eye is really sensitive. I took a spectrum just because I wanted to see the change in some of these pH indicators. And there was bromocresol green, which goes from acid to base. It goes from yellow to green. And the visible spectrum is pretty complex. There's several peaks in that spectrum. And you take a spectrum of the yellow substance, the yellow solution, put a few drops of acid in there, and it turns green, and you take a spectrum of the green. And if you just looked at both of those spectra independently, they would look exactly the same. There really wasn't any difference. It wasn't like a brand new huge peak because of the different color. You put them on top of each other, and right around like the yellow area or the blue area, I don't remember which, it was just a very slight change in the size and shape of one of the peaks. And that was enough to tickle a different pigment in my eye. And so my mind is like, wow, that's a really dramatic color change. But the spectral change really wasn't very dramatic at all. So our eyes are very sensitive to certain color changes. And so these colorimetric tests just take advantage of that. We can detect things with our eye at these color changes down to 1 microgram sometimes. That's a very small amount. This is the one point though that creates problems. It says accuracy improves with experience. Well, improves, that implies that it might not be so good. And so if you're not experienced with the technique, you might give wrong results. Okay, a lot of times these tests will react with the substance, create a complex that's colored, and then that colored substance reacts with oxygen in the air. So we've got a very reactive atmosphere. We base our whole lives on that. I mean, we don't have to deal with consuming our oxidant. We just breathe it in. We only eat fuel, okay? And we breathe in the oxidant. And so the oxidation of our atmosphere is pretty strong. And so a lot of these colorimetric tests, they produce reactive species that are colored. You need to read them in a certain window of time, and then that color is going to change or fade. And so if you're inexperienced and you don't have an idea of what this timing involves, you might make a wrong reading. Like it might be bright orange and then fade to a brownish gray, and you say, well, it was negative for methamphetamine. And then an experienced person looks at it and they see that bright orange and they're like, oh, that's positive for methamphetamine. So this is something that you just need to be cross-trained on to make sure. And of course, the spot test instructions will be very specific. Read after 3 seconds. After 7 seconds, it's no longer valid. And so it'll tell you specifically how to do it. A lot of times these are used as spot developers in thin layer chromatography. So you'll do a small separation on a plate, and then you'll spray a developer and you'll see the spots change color. Let's talk now in the spectral environment, some funny terms that you may not have heard. So scientific terms related to shifts of peaks in a spectrum. Like I said, that bromocresol green spectrum really wasn't a new peak. It shifted a little bit. I'll just say at this point, it shifted to the blue and it got a little stronger. So it's a very subtle change. But if I wanted to describe in scientific terms what I saw, then I would have to say that it's a hypsochromic shift and a hyperchromic development. So it's going to be a taller peak and it's more blue. Okay, so you've never probably heard hypsochromic, but this is wavelength. So if it shifts to short wavelength, it's a hypsochromic shift. If it shifts to long wavelength, it's bathochromic. So that's telling you which direction, to high energy or low energy, that it shifts. And then hypo versus hyper means strongly colored, hyperchromic, weakly colored. If the peak starts to go away, then that's going to be hypochromic. In hypo and hyper, you should have that down from just your background in science, right? You've got hypertonic and hypotonic. We use those for large and small all the time. So a larger peak or a shift to a larger peak would be hyperchromic, and a smaller peak would be hypochromic. How do you remember this? Well, the bathochromic, I just think of red tones and long wavelengths are warm to me. All right, and I like warm baths, right? So bathochromic is a shift towards the red, and that, for me, mentally, this just makes me think of a nice warm bath. Yes?
Where does that prefix come from?
Batho?
Yeah.
I don't know. That's a great question. You stumped me. You want a sticker? To encourage dialogue. So. And hypso, just to cut someone else off the path. I don't know where hypso comes from either. Yes. I heard somebody go, ah!
I was about that.
But I put that little star on there because that's something in the practice test, and it's fair game. The main reason I point this out is not that I just would say shifts to shorter wavelength. That's unambiguous, right? But you'll run across these words in the literature, and so this is just about being, understanding what you're reading. They'll use a hypsochromic shift, and you go, whoa, what is that? Now you know. Let's now talk about the different colorants. So these most of the drugs of abuse are either pale yellow or white powders, and so that's this spot test or colorimetric reaction creates a pigment or a dye or some other kind of colored substance. And we'll talk more about the difference between pigments and dyes when we get to paint and ink analysis, but they're really nothing. I pointed out here to say there's really no chemical difference between a pigment and a dye. It depends upon the solvent that you're putting it in. So a pigment is just not soluble in the solvent. It's just suspended in the solvent, and a dye is soluble in the solvent. That's the only difference between the two and how they're used. So it's not like you look at a molecule and say, oh, that's a pigment. It depends on what you're carrying it with. And so if you're putting a water-soluble colorimetric molecule in an oil-based formulation, and it's going to be a pigment. If you're putting that water-soluble color into a water, it's going to be a dye. Okay, so that's the only difference. Let's talk about these 4 families of colored molecules, dyes or pigments. And these are the families that I'd like for you to know. So there's the triaromethynes or dimethyromethynes, azo dyes, nitro and nitroso dyes, and then the carbonyl dyes. And so here are the 4 families, sort of examples of them. And so this is what I would like for you to know how to do. Is to look at these and see, for triaryl, break it down. 3, what's aryl? Like aromatic rings. Methine is this carbonate in the middle. It's bonded to 3 things. But sometimes that's a carbocation. So you'll see a plus on there. And it'll just have 3 signal bonds, no pi bonds, but it'll have a positive charge because the carbon came in with 4 valence electrons. It's only making 3 bonds. And so it can really only claim 3 electrons. So it's positively charged. It's lost an electron. And that allows this structure to be planar, or attempt to be planar. You really can't make a planar molecule out of these 3 rings because of the hydrogens that come off of them. The hydrogens bump into each other. But they'll try to be planar, and they can't extend that pi cloud through that sort of 3-valent carbon. And you can see then that when you extend the box of those electrons, then their peaks move down into the visible region. So this would be a triarylmethine dye. If I were to remove one of these and put a hydrogen there, it would still be a colored substance, and that would be a diarylmethine. But the point is that it's aromatic rings bonded to a carbon that has 3 valences, 3 covalent bonds. That one may be one of the more difficult ones to recognize. The other difficult one to recognize are just extended pi systems with carbonyls. So these carbonyls on here, and then the extended pies. So you've got rings that are close to each other, and then you've got carbonyl groups. What do the carbonyl groups provide for these systems? In other words, if we want to absorb light in the visible region, those carbonyls bring something to the party. What do they bring? So let's say the substance didn't have those carbonyls. It might have a peak. The homolumal gap might be in the UV, or deep blue. Okay, and so it might be kind of a yellowish substance. You put a carbonyl on there, and now that homolumal gap is closed quite a bit, and now the peak is maybe in the red part of the spectrum or the yellow part of the spectrum. Mm-hmm. So what closed that gap? The carbonyl brought something to the party that now is useful for absorption spectroscopy. It can extend the system some, but it's just a single bond, so it's not extending it very much. It's bringing something else with it. What are the different types of transitions that you have in visible spectroscopy or electronic spectroscopy? So if we were to label these transitions with the I don't want to say it's going to totally give it away, like sigma to sigma star, right? Pi to pi star. What are the kinds of things that we have that we could label these transitions with? Just throw one out if you know it.
Is it like the bonding and anti-bonding things?
Yeah, so you could have like a sigma to pi star. What are all the combinations? Nobody knows? Okay, well, just think about it. MO theory, right? Mm-hmm. What are all the possible ways you can label these molecular orbitals? We'll stick with the diatomic language. I've already told you 2 of them. Pi star. What else? Louder. Sigma star. So there's 4. There's one more that you're missing.
Non-bonding.
What was that?
The non-bonding.
The non-bonding. And so these are 5 possible labels for the different molecular orbitals. And so that's refreshed your knowledge of MO theory and the different ways to label these orbitals. Now, go back to my original question. What does the carbonyl bring to the party?
Is it like the pi?
So it brings a pi in, it brings a sigma, so it's in one more sigma, right? The oxygen's bonded to it. There's also a pi interaction. So it brings a sigma, it brings a pi, and it brings one more thing.
The non-bonding with the lone pair.
Yeah, lone pairs. We don't even draw them. We're so lazy. But every one of these carbonyls has 2 pairs of non-bonding electrons. And those can absorb and go into the cloud. So if we take the carbonyls off, we don't have those non-bonding electrons. We might still have a visible peak. It might be deep, an absorption in the blue region. But now we bring in an oxygen with non-bonding electrons, which are high in energy. And so now the LUMO and the non-bonding electrons are really close together. And so that peak might be in the yellow region or the red region, and we've got a strongly colored substance. So the N to pi star transition is allowed. Now with the non-bonding electrons, you take the carbonyls off, you don't have those non-bonding electrons. And so you have a pi to pi star transition, and those might be further apart. So bringing in the carbonyls, gives us non-bonding electrons that can absorb light. You still need an extended pi cloud to bring it down to the visible. So you've got both. You've got the carbonyls, because just because you have a carbonyl doesn't mean it's a colored substance, right? You got acetone is clear, but acetone doesn't have that extended pi cloud. You put that carbonyl on something like this azulene type structure or purine rings, and you've got the extended pi cloud, and then you've got the carbonyl with the non-bonded electrons. Okay, so those two might be the most difficult to find. The bottom two are super easy to find. So if I show you a colored substance and say, what kind of family is this colored substance in? Is it a nitro type pigment or dye? Is it a carbonyl dye or pigment? Is it a triarylmethine or an azo? Well, here's the azo right here. So this dinitrogen structure is an azo linkage. And then the nitro dyes are right here. Here's the nitro groups. And what do these bring to the party? More non-bonded electrons. And so these are on the oxygens. I can't make my points really small because it'll think I'm doing a long click and it'll mess up. That's why the electrons are so ugly. This sulfonate group, even though it's got non-bonded electrons, these typically don't contribute to the color. They put sulfonates on a lot of these molecules so that they're water soluble. So a lot of the acid-base indicators that we use for titration are sulfonic acids, but the sulfonate is just for water solubility. And so you'll get a sodium salt of this sulfonate group, and it's the azo or the nitro or something like that that actually contributes to the color. Yes? Yeah, it's just hard to see. There is a little negative right there.
The other nitro group.
Oh yeah. So there should be a negative right there. So that's from the book image, so they just left it off, I guess. Okay. And so let's look at some of these reactions. Can you close the door for me, Teresa? Okay, so this one's called the Marquis reagent. And we're actually not shown what the Marquis reagent is. Okay, it's just in this box, Marquis reagent. And, you have amphetamine, which is, not necessarily a drug of abuse. It can be in certain high-powered cold medicines. And then you have methamphetamine with this methyl group. That's the only difference. No wonder it's easy to make in a clandestine lab. You buy a bunch of Sudafed, which is something similar to this, and you do a reaction to put a methyl group on it, and now you have methamphetamine. Okay. So this is quite different. I mean, not very different, but yet with this Marquis reagent, we're able to see the difference in the structure. So what happens, this is a dimerization reaction. So the Marquis reagent takes this carbon on the opposite side of this R group here and activates it in some way so that these molecules join together. And so look, you've got two of these molecules joined together by this carbocation. So it's a dimerization. And that extends the pi cloud and makes it colored. And it's amazing to me that this change in this methyl group causes a color change. This goes from orange-red and then develops into a brown. And then this one just stays orange. And so that would be, again, something that you would have to be trained on, but you could tell the difference between amphetamine and methamphetamine using the Marquis reagent. And so that would be a presumptive test for a controlled substance. So what type of dye is this? Well, it's a carboniamine. It's a diarylmethine. So there's your methine piece. This carbon that has 3 bonds on it, and then you've got the extended cloud with the aromatic rings. You could also do this by process of elimination. I don't see any carbonyls. I don't see any azos. I don't see any nitros. Okay, but I really would like for you to understand this is the aryl pieces and then this carbon in the middle. Okay, so let's go on to another one. Here's some morphine with the Marquis reagent. So the Marquis reagent causes a dimerization of the opioid structure. And also the difference in morphine is in heroin and codeine and thebaine are all down here on these OH groups. And notice these OH groups are not affected by the Marquis reagent. So we should be able to get different colors for heroin, morphine, codeine, thebaine, all these different opioids. Because what it does is it activates this double bond on the bridge side of the molecule. So this little bridge up here, let me do this on the video so that people can follow along when they watch it. Here's the bridge in this opioid structure. And the ring adjacent to the bridge is activated. And it is actually the point of dimerization. So I've taken this and I've drawn it now down here. We've got 2 opioid structures on either side, and those are the activated bonds in this original molecule. And so this has, again, been an extended pi region, and you've got these carbons. Now there's one right here. This is that 3-valent carbon. So this is a diaryl methine, but it's also a carbonyl. And so this one, you might be able to say it could be in either one of those categories. Because it's got carbonyl, but it also has that trivalent carbon. So that gives a violet color. You can react it with acid, and then you create that cation. Then LSD with the Ehrlich's test, and that's using this p-dimethyl aminobenzaldehyde. So this is para dimethyl aminobenzaldehyde, and this right here, carbon on that aldehyde group reacts with this carbon here, and so we stick this p-DMAB onto this part of the LSD structure. So once again, we have a simplification that you would run across in the literature. Instead of drawing the whole structure, we just sort of cut off the piece that doesn't react. And so that's what this little wiggly line is. We're saying we're going to draw that wiggly line and then use it later to show that everything above that line hasn't changed. And it just compresses the way we show this structure. They didn't do a lot of this in organic or any of the other courses you've had. And so when you get out into these more practical fields, you've got to kind of learn how they take shortcuts or you'll be confused. So this DMAB has an aromatic ring on it, okay? And so now we have a diaryl methine. We remove that OH group. We could react it again and make a trimer. Actually, we pull in 2 of those LSD molecules and still have the p-DMAB here. We could remove that proton, and we have the triarylmethine. So So you should. I'm just expecting you to just be able to find all the parts. There's no way I would expect you to draw all that stuff. There's no way I could do it. I'm not just now. If I did research in this area and that was my thing on this particular test, yeah, I could probably just, stop and just write out all of these things. But I'm looking for a recognition level from you guys. Okay, phenols and amines, the Lieberman test. This again extends the pi cloud and is a carbonyl. So down here you have in the final ending a pH dependent color. You've got in acid it's red, in base it's blue, so it's very similar to the litmus test. So you've got those non-bonded electrons on the oxygen and an extended pi cloud. And so the other side is the pH active part, so whether it's protonated for the acid or deprotonated with a sodium ion, you're going to get different colors. Do not be confused by this nitrogen in the middle. That is not an azo. What would it have to be an azo group?
Double nitrogen.
2 nitrogens, yeah. And they'd be double bonded to each other in the middle. This one is the Simon test. It's an inorganic reagent, so it's iron bonded to 5 nitrile groups here. And so this again would be for amphetamine or methamphetamine. This reacts, the amine reacts with this acetaldehyde, and then we have this piece on there, and that's the active carbon for this reaction with the Simon test. And so this inorganic substance attaches to that carbon and creates this piece here. And then you can react that with water, and this blue piece, it takes those carbons off of the nitrogen, and so it extends and grabs this piece